Thank you very much. And I would like to start with thanking the many collaborators of the stuff that I'm going to present today, listed all here. I will not go through the individual names, but they contributed bits and pieces to all the stuff that I'm presenting here. It's kind of, so to say, in part old stuff that I was doing because I was trying to stick to this topic of the workshop, the boundary conditions. And so I apologize if some of this looks a little bit old-fashioned, but I'll try to make the connection to what we're discussing here as we move along. And like everyone, I will start with a little sketch. That's how I imagine a typical situation when we talk about charges at interfaces. So we have an interface between two regions. That could be a bulk and a second bulk, or that could be a bulk and vacuum if you're talking about a surface. And the idea, of course, is that there is some extra charge here at the interface. And as Axel correctly pointed out, of course, the entire system is uncharged. So whatever we have as an excess charge here in the surface region needs to be compensated by the stuff that is outside. The main reason why we want to use boundary conditions is that this happens on a nanometer to micrometer length scale, which basically means that in atomistic calculations, we can't capture this in an efficient way. So if we zoom into the region of interest, where really the surface charging is going on, we have a situation where whatever complicated stuff we have inside, we see the surrounding, what happens outside, basically through boundary conditions. In particular, the potential at either side of the interface, the fields, and of course, the change in field between the left and right-hand side must somehow be related to the charge. In reality, the charge is typically fixed by the Fermi level in the system. So as we change the conditions, charge may move in or out of that region according to a thermodynamic equilibrium. Now that's one way of looking at this, and of course then we can start doing the simulations and wonder how the boundary conditions influence what is going on inside. There is a different way of looking at this, basically looking at the same thing from the outside and say, okay, if we come with certain boundary conditions here, what is the system doing inside in order to change the boundary conditions on the other side? Yeah? So that is more or less the perspective that you need for large-scale modeling. And the question is, can we come up with a simplified surrogate model in this region that it behaves exactly as our real system, but captures the key features in particular for the electrostatics? That's the way of thinking that I would like to present in this talk. And this links immediately to this boundary artifacts. Instead of thinking about the simulation as, oh, we have the wrong boundary conditions, we need to correct for this, we can also ask the question, okay, how does the system interact with the boundaries, yeah? And how can we use this understanding in order to simplify also the modeling at the larger scale? So what are the key properties that we need to extract from our atomistic simulations in order to be useful for large-scale simulations? And I will, as I said, run a little bit about different topics. The first one will be charged systems, in particular point defects, because it illustrates nicely the challenges that we have there. Then I will talk a little bit about electrostatics at surfaces, interfaces, and slabs. And last, I will briefly touch a little bit on the point of the type of electrostatics that is described by DFT and how we might be able to model this again in a more surrogate way in order to move forward towards including these kind of nicely described electrostatics in coarse-grained simulations. Okay, point defects is where I'm really coming from, and the motivation is in part also because those bulk regions, if they're semiconductors, the charging is determined by the point defects. They're crystalline materials, so typically when we just want to understand the crystalline materials, 3D periodic boundary conditions is the perfect thing to do. If you want to describe a single defect in such a system, periodic boundary conditions are a problem, yeah? Because the single defect is not described, cannot be described compatible with periodic boundary conditions. What is done is that we take a larger region of our crystal, you know, not a single unit cell, but multiple super unit cells, put a single defect inside, and then again apply periodic boundary conditions so that we replace the single defect in our large system by a periodic array of defects. And of course, in principle, we can just make the supercell larger and larger and larger, and then converge to the limit of an isolated defect not interacting with anything else. In practice, we are limited to order of 100 to 1,000 atoms, depending a little bit on the level of theory that you want to apply and what you want to look at. And that is not necessarily sufficient to completely prevent defect-defect interactions. Is that the only way we can go? Of course not. We could also do some kind of cluster and embedding of this entire thing, or we could use Green's function technique. The main issue is that it does not solve the problem, because the physical effects that mediate defect-defect interactions in such a supercell approach are the same that we would have to worry about when we do some kind of embedding in order to capture those features, or the kind of ingredients that we would have to put into our Green's function in order to properly capture this coupling. So the physical effects that make the defect-defect interactions are always there, and we have a choice of whether we want to deal this in a supercell geometry or in alternative geometries. The main thing is that this requires a significant amount of expertise, while here we can basically start right away and think afterwards, so to say, how we deal with the different effects systematically, one after the other. Okay. So what are these defect-defect interactions that I'm talking about? The first thing, if you think about a defect, in particular in a semiconductor, is that there might be a wave function associated with this, and this wave function has a finite extent. And if your supercell is too small, you have overlap of those defect wave functions with neighboring cells. Yeah? These are quantum effects. Fortunately, we know that for states that are located in the band gap of a semiconductor, the decay qualitatively goes exponentially down. So there's a good chance of doing that brute force. Secondly, we know how to correct the first order effect, because that is related to the band dispersion of the bands that arise from those defect states in the band gap. And by a careful way of doing decay point integration, we can correct out for these effects to first order in a reasonably good approach. So usually, they are there, but they're not the ones that give rise to the largest issues, except if we have particularly delocalized defect states close to the band edge. Then, of course, a defect may locally strain the lattice, expand it or reduce it. We know that this must decay like 1 over r to the cube. In principle, one can do corrections for this. In practice, for most of the defects that we are looking at, the effect is very small, because those strain effects typically are on the order of 10 millielectron volt, and compared to the many other errors that we have in such calculations, that's usually negligible. And that leaves us with the Coulomb interactions if we have charge defects. And for this, because they decay very slowly, like 1 over r, it's very, very clear that some corrections are needed. Now, if we go back to the DFT code and see how the electrostatics is treated in the DFT code in periodic boundary conditions, it's mainly contained in the electrostatic potential of the material. Because we have 3 periodic boundary conditions, we make a Fourier transform, and then it's very simple to solve the Poisson equation. You come with the charge density that contains the electrons and also the nuclei. You multiply this with the Coulomb potential in reciprocal space, which is a 4 pi over g squared, and then you get the electrostatic potential, and then you plug this into your formula for the electrostatic energy. Very, very easy. It's essentially dot products of your sum over the reciprocal lattice vectors. Of course, this only works if g is not 0, because if g is 0, this clearly is ill-defined. So what is done in practice is that we just set the average electrostatic potential to 0. That's our boundary condition. So when we say we have charged systems in DFT, it basically means that our boundary conditions are periodic boundary conditions for everything but the average electrostatic potential, and the average electrostatic, by definition, is set to 0. That's how we work with it. Now, one way of understanding this, and this is what is often discussed, one way of looking at this is, well, this corresponds more or less to saying that if the charge is non-zero, in order to make it 0, we just add something that compensates the g equals 0 component. Yeah? And this is this wording that we introduce a homogeneous background in order to compensate the charge. Technically, we don't do this, but it's mathematically equivalent to doing that. And this is also, when you look at the electrostatic potential, it looks as if there was a homogeneous background in the places where we do not have the excess charges. And I don't think that I have a picture for this, but this, for example, leads to a parabolic behavior of the electrostatic potential when you move far away of defect centers. That's one thing. The other thing is, now, if you think of adding some extra charge into the system, then of course you can say, like, oh, it's very easy, we know exactly how it is by looking at the electrostatic potential. That's not quite true, because when we add some extra charge to the system, the electrons will react to this. They will start to screenate. So instead of just having our electron density plus the extra charge, there will also be changes in the electron density. And this electron density is not only contained in the electrostatic energy, but it also affects the exchange correlation functional, the exchange correlation part, or the kinetic energy part, and all the other parts. So even though, in principle, the key effects are contained in the electrostatic potential, it's not the only thing that we need to consider if we want to understand how DFT energetically describes all those screening effects. So we have to think of something else. And for this, we go back to the start. So assume that we have some kind of system, some kind of defect system with a defect level that is currently empty. So we might add an electron, or if there was an electron before, we remove it. And in the first step, we just put extra charge onto this one level without allowing for any relaxation. And this provides us a bare charge density that will be important for understanding the rest. Now, in the second step, we say, okay, now there is this extra charge. Let the electrons do whatever they want to do. Let's the electrons relax, and if they have an ionic system, maybe also let the ion relax to new position. And this gives rise to a change in the electrostatic potential that we expect directly from the DFT. And when we have this change in this electrostatic potential, which now contains all the screening effect, and combine that with the unfortunately unreadable bare charge density, then we can compute an electrostatic energy which has exactly the energetics of the DFT, because all the screening effects are contained in the change in potential, but we don't include the screening effects additionally in the charge, which would have a double counting effect for the entire thing. Now that, in principle, can be done also for an isolated defect. However, we have periodic boundary condition, and that is the third step. Then, after we have understood how to treat electrostatics, then we introduce the periodicity and the background, and we get a periodic potential, which is essentially just the superposition of these isolated potentials. Now, in principle, we can correct for this artificial effect by just subtracting the contribution of the periodic potential, the repeated images, from the periodic potential that we have, by just leaving, so to say, then the effect of the single potential. In practice, it's a bit difficult because we actually do not know this isolated potential, because the only thing that we can see is the periodic superposition of those potentials. However, we know in the system how the long-range behavior of those defect states behaves, because we know that this is solely determined by the total amount of charge contained in the defect if it's well localized, and the macroscopic screening effects of the material where this is living in, and we can model this quite nicely. It turns out that if we just are able to model nicely the long-range behavior, all the short-range deviations from this long-range behavior are nicely localized around the defect, so they're captured quite accurately within the supercell that we can afford. So the only thing that we need to care for is the long-range effects that cause all those problems. In practice, this turns out then to give us a correction which is composed of a lattice energy that we can take from the simplified model that just describes the long-range effects. And secondly, in alignment term, I said that we set the average electrostatic potential to 0. If you have two potentials which have the same long-range behavior but different short-range behavior, their average electrostatic potential may shift, and we need to take into account this shift in the potential by aligning our long-range model to the actual difference in the DFT. Nicely, if we do this correctly, it also captures the next order of effects. So while the correction accounts for the monopole-monopole interaction in presence of the homogeneous background, this alignment term also accounts for quadrupole-monopole interactions and dipole-dipole interactions that might be contained in the system. Good. In practice, this is very nice. This is the original thing here plotted now as 1 over the linear dimension of our supercell to capture this 1 over R behavior if you don't apply corrections for gallium vacancy and gallium arsenides without ionic screening in this case in order to really focus on the electrostatic effects. You see this strong increase if you don't apply the corrections. And while you might be able to extrapolate to infinity here, you have a few cases which don't fall on this curve. If you apply the corrections, that's these green dots over here, you see that you're nicely within order of 0.1 EV can converge to the correct value. That agrees then also with the value that you would extrapolate if you trust extrapolation here. So that's how it works for charge point defects. Now let's move on. What can we do with these defect calculations beyond just calculating their formation energies? And one of the interesting things is to look at charge transitions. And that somehow relates to electron transfer also in electrochemistry. You may have seen a similar sketch, I think in the last workshop where we actually were talking about Marcos' theory of electron transfer, exactly the same sketch, exactly the same principle. Here, the typical situation is that we have a relaxation coordinate. So if you have the a defect in one charge state, say +1, it has a certain atomic geometry. If you have it in the +0 charge state, we have it in a different geometry. So this axis here just captures changes in the geometry, generalized reaction coordinate. If we would move from the +1 up here, for example, by emitting a hole or by capturing an electron, there is an energy difference that in particular could be provided by an optical photon. So this vertical transition here basically relates to the optical excitations in this material. And reversely, if you go from a higher state to a lower state under the emission of a photon, that would relate to the emission of photons. So this is the kind of stuff that we can get from these diagrams. In addition, and that is probably closer to what we have in Marcos' theory, we could thermally excite from this state up to this point here, where we would be able to capture a hole without emitting a photon or without doing anything. Then we would end up on this second curve here in a much higher state, and thermal vibrations would then bring us down here, which means that this energy that is contained in this state here will be released into heat. And of course, that is a very important loss process for all the optoelectronic devices, solar cells, LEDs, and so on. So that's why people really care about this. Okay, how is that related to corrections? Well, we know that in order to get the energies of those minima right, we need to apply corrections. What about the rest of those curves when you want to compute this? And instead of making long speculations, I will just show you how it looks like. This is a very simple toy example, the oxygen vacancy in magnesium oxides at a very low level. It's just a toy example. You see here different charge states, the Q equals 0, the Q equals +1, the Q equals +2, calculated in different supercell sizes, starting from a 64 atom runs less than a minute, to a 5 by 5 by 5 with 1,000 atoms that runs for several hours. And on the horizontal coordinate, I have a configuration coordinate now labeled with the ionic charge, so that this point here corresponds to this structure, the relaxed structure in the +1 charge state. This here corresponds to the relaxed structure in the +2 charge states. In between, we just linear interpolate. But from +2 to +3, we just extrapolate basically this part here to this regime here. And similar here, we extrapolate from 0 to 1 the coordinates in the structure linearly to this regime here just to see a little bit the effect. Now you immediately also see that the charge 0 has no corrections, needs no corrections in the stable state, but as we move away in the configuration, you start to see a significant dependence on the supercell size. For the +1, you already see this in the minimum that can be corrected with the corrections that I've just presented. The +2 even larger, so that is known. You also see that this deviation increases as we move away from the minima. What is most important here is if you think about those non-reactive barriers, those hole capture barriers. If you look at the crossing points without any corrections, you see that there is a very, very dramatic drift of this crossing point with respect to the relevant minimum over here, on the order of a couple of eV when we go from the small to the large cells. Now, you have to remind, this is thermal barriers. So if you make an error of several eV in a thermal barrier, that can completely bring you from irrelevant to highly relevant if you get that wrong. So it's very important to be able to correct these things more accurately. So how do we do this? Let me first show what we could do with extrapolation. If we plot this again as 1 over L in order to extrapolate nicely, you see that without any corrections, you have this very, very nice linear dependence. So you could be tempted to just extrapolate to infinite size. Similar, if you just apply the charge corrections for the minimum for each of these curves separately, you get the red curve, and you also are tempted to extrapolate to the minimum. And if you look at the corrected value obtained from the corrections that I'll show in a moment, and you see that they nicely all cross in the same point, except that this is not at infinite supercell size, which is over here at 0. Even worse, I was saying that we are looking here at a barrier, the difference between the minimum of a parabola, or approximately parabola, and a point higher on that curve. And if you just blindly extrapolate, we get negative values, which is not only physical nonsense, it's a mathematical impossibility. So this kind of extrapolation is complete bullshit, even though it looks very nice. In this particular case, we know that it's bullshit. If that would happen at higher energies, people might not notice and say like, oh, we've extrapolated, everything is fine. Okay, so
is the point here that the true, because presumably if I had a 1,000 by 1,000 by 1,000 supercell, it would fall on the corrected value line?
So if we take a huge cell, my correction, and I will show you in a moment why I believe this is the correct value, will be somewhere here around 0.15 or so.
So the 1 over n dependence is just not...
The 1 over n dependence, it looks like a 1 over n dependence, but at some point it must curve here. And that basically is because here it still seems to go linearly, but in the vicinity of this thing here, it must somehow flatten out. But if you just look at the raw data, you don't see that. Yeah? So that's very important when one does these empirical schemes, that one really needs to understand what is going on and how the asymptotic behavior is, because otherwise one is very easily misguided by the nice quality of the fit and saying, okay, I understand what is going on here, and I extrapolate to something that is. I will demonstrate this for another case for the surfaces as well. Okay, so how do we construct corrections in this case? Let's go back to the scheme. Let's first start with the case where we have the configuration in the fully relaxed minimum. So that is basically the same that I said before. We introduce a charge into a neutral system, allow the full dielectric response. Ions relax, electrons relax. We get a change in the potential. We introduce periodicity in background. And from this, in principle, we can construct the energy correction for the minimum. And then what we do is that we change the charge state, which means that we add another electron to this pre-charged system. But because we don't change the position of the atoms, we only have the electronic response, not the ionic response. And so this gives us a different change in the potential that only sees the dielectric constant due to the electronic screening. And again, we can then introduce periodicity in background. And now we have all the ingredients in order to construct a correction for the combined system, where part of this is screened by the ionic screening and part of the charge is only screened electronically. The full screening has this form. The electronic screening part for the second extra charge has this form. But then there is also this very important coupling term, which says that this extra charge here sees the error in the potential due to periodic boundary conditions coming from the first charge. And this here is basically mixing now the extra charge and the initial charge. And this is why you can't get this by a clever combination of the original charge combinations. You really need to take into account that you have two different charges with two different screenings. If you put this together in this way, where you just take this part here and this part here, you get a correction for the vertical transition. This is the paper that we did together with Tomoyaga and L. The correction for the entire thing more or less appeared at the same time. That was by Alfredo and co-workers, in particular by Stefano. So it's exactly the same conceptual idea, even though the formulation is slightly different. So how does this work? And how do we deal then with the intermediate configurations? Very easy. We have a linear interpolation of the coordinates. We know, because the ionic screening is more or less driven by the relaxation of the ions, that the long-range potential to very good approximation is then a linear interpolation of the corresponding long-range potential at the different charge states. And because the potentials by themselves are linear in the charges, we can relate this down to basically the potential of a linear interpolation of the charges themselves. Of course, always using the correct amount of screening. If we put everything together and assume that the shape of the charge of the ionic part of this first part and the electronic part is the same, we get a very, very simplified formula which has two key ingredients. That's the correct one over lattice constant scaling. This here is more or less the traditional charge correction, now taking the final states as the charge. And then this is the key point which makes the deviation of those curves, where you see it depends quadratically on the difference between the charge that determines the ionic configuration and the actual total charge that we use for computing the energy. And the prefactor is the difference between the two screening constants. And that is why, sort of, if you go away, even at zero charge, where this part here vanishes, you have a deviation in the curve. This is how it looks like when we apply the corrections. This is the Q+1 charge state. The solid lines are the uncorrected ones. The dashed lines are the corrected ones. And that is better than I had hoped for. Yeah, that's really a beautiful, perfect correction of those effects. Really way up to large deviations. If we do the same thing for the +2, it looks not as perfect, but reasonably well up to this point here. And then it starts to deviate. And I was first a bit worried about this, but then one has to think about what this actually means. If we have the +2 charge states and compare that to the +1 charge state, we also have to consider that we have a reference. And the reference, or the reservoir for the charge in this case, is the valence band, so this is holes. So we can think of this here essentially being a +1 charge state and a hole very, very far away. Now, what happens here is that as we move to the point where the +2 gets less stable than the +1 and the hole very far away, is that within our finite-size supercalculation, the DFT calculation notices that actually the more stable state would be to remove one of the holes from this defect, or in other words, to capture from the valence band an electron and put this into the defect. And this starts more or less right at the point where this crossing thing happens. And we can't correct for this because the states get increasingly delocalized. So our assumption that everything is nicely localized is going down. And you see this if you look at the potentials actually also in the calculations. So I did not try to correct this for here. In principle, by using a more smeared out charge for the higher charge states, one can also capture these kind of effects. So now, of course, you may ask, sort of say, is this of any relevance to electrochemistry? And I can show you one example, very recent example. I think it's now an archive, and I apologize for the bad quality because I copied this from the archive version, where Zhen Yu did a similar kind of thinking, except that this is now the free energy curves from MD simulations, including water, for iron atoms at different charge states in order to determine the Marcos barrier. And he used finite supercells, not so small. I think it was order of 30 by 30 by 30 angstroms. So not something that we would usually consider a very small cell. But even here, you see a very, very noticeable impact of the charge corrections. And it turned out, even though I only showed you one example, if you do this at different different box sizes, They are very important in order to get converged results. So even for electrochemistry, if you want to go for half-cell Marcus barrier calculations, you need to take into account that these corrections are important if you want to get accurate results. And again, here we're talking about a couple of tenths of an MeV, even in this relatively large cells, in water, which has a dielectric constant of 80. Yeah? And the main thing here really comes from the fact that it is the difference between the static and the full dielectric constant, and the static dielectric constant of water is small enough to make a sizable effect even in these large cells. Okay, good. Let me move a little bit on to interfaces. In principle, the same game. We have a periodic array of defects now sitting in a periodic array of repeated slabs. That's how we usually construct supercell sizes. It's, in principle, a very similar situation to what we have before, except that the dielectric screening is a little bit more complicated because the dielectric constant varies as a function of space, which in the most simple case can be modeled by assuming a certain dielectric profile as a function of the z-coordinate. And now, in principle, we can compare this artificial situation to the situation that we really want, which either might be that we have a defect sitting at the surface of a very large bulk, where the dielectric profile would look like this, or in the case where we have thin layers, in particular of 2D materials, where the isolated case might actually still correspond to a finite layer, but without the presence of the neighboring defects. So in principle, we can construct a correction in exactly the same way, except that we now have to take into account these dielectric profiles. In our code, we use the image charge method as a way of discretizing the underlying differential equation. As a discretization, it's really, really bad for computing differences between such a situation and such a situation, because we can treat this exactly in the same way and make the same kind of discretization errors. The error cancellation is really fantastic, and we can get very easily well-converged calculations independent of the type of dielectric profile that we assume here, and independent how we distribute the charges over this region here. Again, I show you some examples. One possibility in this case is that we increase the vacuum size. If you do this without correction, you get this well-known linear divergence of the electrostatic energy, because you essentially build up a capacitor. With the corrections, everything converges very, very quickly. Similar, if you would just increase the lateral size, the energy has a quite significant dependence, including the corrections that saturates quite easily. The small deviations here, we understand where they come from, but also for this lateral thing, which is actually more difficult to capture, these corrections work really very, very nicely. One small comment, you might think that in this case you actually can do it brute force by just increasing the supercell. However, if you consider the electrostatic of the system, if you just take a 2D elongation of a charged system with a homogeneous background, one can show that there is a logarithmic divergence of the energy. So even though this looks very nicely, in practice it will never converge if you don't apply corrections. Now, having that nice little tool for corrections, we can also make a small model study, emphasizing again the importance of understanding the electrostatics. Assume that we had such a cell, and if you do it one-dimensional, we know it diverges. If you do it two-dimensional, we know it diverges. In principle, if we do it in all three directions at the same time, we should get a convergent behavior. The only question is, if this goes linear up and this goes logarithmically down, if we now do it at the same time, what will be the behavior be? And similarly, does this depend on how we start? Does it depend on the thickness of the slab, a small one, a medium one, or a thick one? Does it depend on whether we put the charge on top or in the center? Does it depend whether we start with something which is very wide to begin with, or which has a lot of vacuum to begin with? And before I show the results, I would like everyone to briefly try to imagine how they think this curve looks like. What is your expectation? And if you now have a mental picture, look at this. This is now all those different systems plotted as 1 over alpha, because it's a model toy system. I know what the exact answer is. This is this one here. So we basically just plot the errors in the finite size. And you see it goes all over the place. We have situations where it linearly increases, then turns up. We have situations where it linearly increases and then flattens out. We have situations where it goes up and down. We have situations where it goes first down and up. The problem in all this is that if you don't have the corrections, and I have made estimates here of what you can actually do in DFT. If you would just look at this data in DFT, this is what you would see. And if you would now assume, look, this is such a simple situation, we can just make a low-order polynomial in order to fit this, this is what you would get. This is the true answer, and all those extrapolations go wrong. The fits look perfect. You would not see a single problem by just looking at the fits. So you really need to understand the electrostatics of those systems before you start to apply empirical corrections, because they can be highly misleading if you don't know what you're doing. Okay, I will skip this. I will move on to a slightly different setup. So far, all the design was we have a charge and we have a homogeneous background, including those slabs here. Now, one alternative possibility, because we now have a vacuum where we can do whatever we want, is that we put a counter electrode here and leave the charge over here. This has the advantage that if we keep the counter electrode in place, we can play with the vacuum thickness, nothing happens. The downside is that we get very, very strong fields, and we've implemented this kind of idea that we replace the homogeneous background by a counter charge in the vacuum in terms of a generalized dipole correction. So if you just kind of turn the axis here on the horizontal side and look at the, again, toy system, aluminum slab, 6 layers, we can apply charges leading to very, very high fields here, 10 to the 11 volts per meter, with a voltage drop within the supercell of almost 100 volts, without getting into trouble with the electronic convergence or anything. So we really can simulate in this way very, very large fields. Why would we want to do this? Because there's a situation where this matters, and one of them is atom probe tomography. I assume that not everyone is familiar with atom probe tomography. Is everyone familiar with atom probe tomography? No? Okay, then I briefly explain. It's a very, very cute experiment. You take a material with many different elements and cut out a needle-shaped specimen from this material. Needle-shaped means with a tip diameter on the order of 100 nanometer, and then a couple of micron long. Then you plug this into your instrument and apply a high voltage of a few kilovolts, using a counter electrode, which typically is a couple of micron away. This large voltage concentrated on a tip with such a small curvature creates an electric field that is very, very high. So high, and you can estimate this to be on the order of 10 to the 10 to 10 to the 11 volts per meter, which means 1 to 10 volts per angstrom. And this field is so high that single atoms can ionize, fly away towards the counter electrode. To make this a useful instrument, you place here a position-sensitive detector, and you additionally trigger those events by light or voltage pulses, so that you can measure the time of flight between your pulse and the arrival on the detector, which means that you have a time of flight mass spectrometer, which means that you can identify the chemical identity of that particular ion. And then you do this for many, many, many atoms. Order of 10 to the 6 million to a billion atoms can be collected. And now, since you know the chemical identity and you know where this was hit on the detector, and because of the electrostatic condition, it more or less is a point projection of the atoms at the tip here and the detector here, and because the distance here is about 1 million longer than this direction, you get a magnification by a factor of 1 million, which means that you can resolve easily sub-nanometer distances on your detector. And this allows you to reconstruct the positions of all those atoms that you have detected in 3D space, knowing atom by atom where they were originally, with a resolution sub-nanometer, and then it depends a little bit on the details of the experiment. Now, the main motivation why I went into this is exactly to understand what is the resolution limits, what are the artifacts in these things, in order to improve the reconstruction of those tips, and be able to tell apart real things that come from the distribution of atoms before we tried the experiment and the effects that happen during the experiments, and thus are artifacts of this method. And in some sense, it's again related to electrochemistry, because what we are looking at is that we transfer electrons from an atom sitting at or in the surface to the surface here, create an ion that goes away, that more or less is the same as metal corrosion, except that we don't have an electrolyte. So this is electrochemistry in the dry, driven entirely by the strong fields that we can simulate with our things. There is, by the way, also an alternative mechanism where we ionize atoms which are a bit farther away. There, the electron dynamics is entirely determined by tunneling. We also have theories for this. I will not tell this, but it also requires the same type of boundary condition with very high fields. The nice thing about field evaporation is that the nuclear motion drives the electron dynamics. So we can just do a standard DFT approach in order to understand the energetics of these events. And this is now the visualization of such a minimum energy path for desorption from an atom that sits at a step on an aluminum surface. So we have here 111 type facets here. This is a 100 microfacet. And so this basically forms a step here. The field is going in this direction. And I've just repeatedly plotted the optimal position as we pull out the atom. Now, there's a few of interesting things to observe here. The first one is that if you carefully follow the trajectory, it does not go straight off the surface, which is one of the key assumptions in the reconstruction, that wherever we come from, it goes straight. It does not. There is rollover. This is observable in experiment as an accumulation of density somewhere on the detector, and we reproduce this effect from our DFT calculation. Secondly, we have the collective motion of the atoms. So if you want to understand this process, it's not sufficient to just look at the atom that leaves. You also need to consider what the other atoms are doing. And thirdly, we observed that this sequence here, no matter what atom we take, always is a sequence of bond breaking, one after the other. And it turns out that the rate determining barrier is always the first bond breaking event. Once the first bond is breaking, everything else goes very, very quickly at the conditions that we have in field evaporation in this experiment, where the barrier has to be very, very low, order of 0.1 to 0.5 eV, in order to be able to be triggered by these voltage or laser pulses. And I could tell a lot of this. I just want to pick out one particular aspect here, and that is the evolution of the barrier as we change the field, because this is one of the things that leaves also measurable traces in the experiment. If you just look here at the binding curves at different fields, this is 0.5, this is 1, this is 1.5, this is 2 eV. For I think this is an add atom on aluminum. You see that the barrier systematically goes down. And of course, it would be an interesting question to understand how exactly does this barrier go down as we increase the field. So how does the barrier couple to the boundary conditions that we apply? Now, looking at this curve here is not very insightful. We can turn this and just, instead of looking at the energies, looking at the forces, basically the first derivatives of those curves. And because it shows an interesting effect. This is now, it's unfortunately a different system. This is I think this is the step atom. But if you look at the forces, this would be outward forces, this would be inward forces. When the force first hits the zero, this is where the minimum is. This is where the maximum of the curve is, and you immediately see that, so to say, if you integrate the force between minimum and maximum, this area here basically corresponds to the barrier. Now, by just staring at these curves here, you also see that close to the region, to the fields where the barrier vanishes, it's more or less a systematic upward shift of the entire curve. So basically, the field pulls on this atom in a systematic way, no matter where exactly it is on the trajectory. And this allows to make very simplified models of how this force develops as a function of field, just a linear shift with a prefactor that has the dimension of a charge. And if you have such a simplified assumption in the vicinity here, you can extrapolate immediately from a single calculation the zero barrier field, so the field where the barrier vanishes, and you can also analytically describe how the barrier would evolve. The interesting thing is this prefactor here, because if you think about this, this is basically how the charge changes as a function of applied field. And since we know that the force, how the force changes as a function of field, is that the force is the derivative of the energy with respect to the reaction coordinate, we can exchange the order of this. And it basically means that we have to look how the energy changes as a function of field as we vary the coordinate. This here, however, is the surface dipole. So we actually get the required parameter by just making a single of those curves. Look how the dipole changes as a function of reaction coordinate, and that's why it's important that it's a collective coordinate. It's not a single, but it's a kind of effective charge for the entire motion that happens here. If we plot this here now as a function of reaction coordinate for different fields, then we see that in the vicinity of where the barrier finally happens, this is reasonably constant. So our assumption that everything shifts nicely is also fulfilled. Interestingly, this is aluminum, where you ultimately end up with a +1 ion that leaves the surface. The effective charge for the barrier is a fraction of this. And there were many models that tried to explain all those things always with the formal charges. Either the +1 is the first ionization state, or the +3, which is what happens in most of the cases really as the final ion. Looking at this with DFT really gives you an understanding of what really matters for determining this. It also means that the electron transfer actually happens gradually as the evaporation evolves. And I think there's a similar situation in many of those electrochemically catalyzed reactions where the actual electron transfer is not a single sudden step, but it happens as the atoms evolve. And using this kind of understanding helps also to understand how the barriers vanish. I will skip over this very, very nice thing here and come to the conclusions. My understanding here is that if we have simulations and we try to understand how the boundary conditions matter for what we see in the simulation, this is at the same time also teaching us a little bit how to include our results into large-scale simulations. And I think this is really an important way to think about these simulations. We don't have to worry too much about wrong boundary effects. We really just need to understand how the boundary effects interplay with what happens inside the simulation, because this is key information or key insight for actually doing a larger scale modeling in the end. If you want to understand charge systems, you have to understand the electrostatics. I couldn't do this. This was a little bit directed to working group 1. We have also good ways of understanding DFT electrostatics with local quantities. Sorry that I didn't manage to do this. Thank you for your attention.